Hi, I'm Joey. So I have on this slide, introduce yourself, but I don't want to spend too much time on it. The gist is I'm a maker and a hardware hacker, and lately something of a product designer. In fact, I designed and shipped a product that some in this audience might recognize, SensorWatch, which launched on CrowdSupply and ended up shipping about 1,500 units so far. SensorWatch is a board swap that goes inside this classic Casio wristwatch. It gives it an ARM Cortex brain and some really cool features for sensing things about the world around you. What I have to share today comes from some lessons that I learned while making this gadget. Still, rather than jump right into the watch, let me first weave you a story. Let's say you're brainstorming a new gadget that you want to make and sell. Let's say it's a hackable clock with an LCD and some environment sensing features in the form of a BME280 sensor. You wanted to do lots of things, so you decide to give it a beefy microcontroller like the SAM-D21. You also want it to be battery powered so that folks can put it in different places and not worry about running a cord to it all the time. In fact, to start prototyping, you grab a battery-powered SAM-D21 dev board like this Feather M0. It has a NeoPixel, which you like for status indication, and then from there you add some things to it. You naturally add your BME280 temperature and humidity sensor. You also want excellent timekeeping, so you add a DS3231 real-time clock. It's a clock, which means you want it to have an alarm, so you add this I2S audio amplifier, which you can plug into a speaker. And of course, you need a display, so you add a segment LCD glass, like this oddly specific LCD, which requires an I2C segment LCD controller chip to drive it. Okay, so you start prototyping, and everything seems to be going great. You love this little hackable clock, and you're certain that once you design a board that incorporates all of these features, you're going to have a hit product on your hands. You quickly realize the DS3231 is a huge chip, and it's going to take up way too much board space on your tiny clock. Then it turns out the I2S DAC that you wanted to use is out of stock and not coming back till 2025. It also turns out that your NeoPixel eats about 1 milliamp of current, even when it's not lit, which is going to kill your battery life. And to top it all off, you realize all these things are going to add up to a BOM cost that is way too expensive, which is going to limit the audience of people who want to buy it. Okay, telling this story pains me because I've done this a bunch of times. I have thrown the kitchen sink at a design only to realize I need to sell it for $200 just to break even. To quote the late night infomercials, there's gotta be a better way. That's where this talk comes in. I'm calling it making the most of your microcontroller because it is aimed at a specific kind of device, the kind of device that I have some experience making, which is an embedded device that runs on a microcontroller. Before we dive in though, a quick aside on, what is a microcontroller? Because we use these dev boards all the time, but it's worth unpacking it just a bit. This is the SAM-D21 at the heart of the Feather M0 board we've been talking about. And in essence, it's a little computer. But what is a computer? Okay, this is a digression, I admit, but it's a short one, and I promise it's going to be worth it. A couple of years back, I assembled this RC2014 kit computer for fun. It's a retro computer, designed after the kind of kit you might have built in the early 1980s or late 1970s if you were ahead of the curve. At its heart is this Z80 CPU. And on its face, it kind of resembles the thing we were looking at a second ago. It's a chip, and it has a lot of pins. But the thing of it is, this is not a little computer. It's just a CPU. There's no ROM for storing program code or RAM for keeping track of variables in memory. You have to add those on as additional boards and somehow connect them to the CPU. In fact, most of the pins on the Z80 are dedicated solely to talking to those additional boards. You can see that in this block diagram at the right, which shows how the CPU interacts with the ROM and the RAM over address, data, and control buses. Eventually, if you get enough of these boards together and you connect them, you do end up with a little computer. Still, even at this point, it can't do something like read a button or blink an LED. You still need to add peripheral cards, like this digital I/O module, to be able to read or write things to the real world. But once you've done that, you can, in fact, get to Blinky with this little computer. Okay, question. Why do I bring all this up? What is the point of this 101 level digression, except to shill for the RC2014? Well, I bring it up as a compare and contrast with the SAM-D21 microcontroller that we've been looking at. When I say a microcontroller is like a little computer, I mean to say it has all of those parts we talked about right there inside the chip. On the right is the RC2014 block diagram, and on the left, a block diagram of the SAM-D21 microcontroller. If you look closely, right at the top left, this thing right here is a Cortex M0 Plus processor, which fulfills the same role as our Z80 CPU from before. At the top of the D21's block diagram, we have RAM and non-volatile memory that fulfill the same role as our ROM and RAM boards on the retro computer. They're all connected by this high-speed bus matrix, which fulfills a very similar role to the address, data, and control buses from before. But that's not the reason I'm showing you this. I'm showing you this because of all at the bottom here, the blocks in blue, where you get not just the ability to read a button or blink an LED, but all of these peripherals. Serial communications interface, timer counters with waveform output, a 20-channel analog to digital converter, analog comparators, a DAC, touch inputs, and on and on. I bring it up because I want you to look at a block diagram like this, and I want you to imagine it as a bunch of free stuff that came attached to your little computer. That way you can look closely at it and think, why buy a thing if we already have a thing? Okay, so that's the background to what I want to talk about today. The TLDR is that if you're building a gadget with one of these little computers, odds are it has stuff inside that's going to be useful. Some of it might be fit for your purpose. Some of it you might be able to bend to your needs. Either way, you might be able to get away with using that stuff instead of adding other stuff. This will help you save board space, avoid parts shortages, simplify your design, lower BOM costs, and live happily ever after. I also want to offer one big caveat here before we get started. This talk is mostly going to focus on microchips, SAM-D, and SAM-L series of chips, just because those are the ones that I'm most familiar with. But these same guidelines apply to lots of microcontrollers. Pulling off tricks like this with other chips might require a deeper dive into their datasheets, but these same broad guidelines will likely still apply. Okay, so with that as background and 6 minutes in, welcome to my talk. Wait, what? Welcome to my talk. So this talk is based on lessons learned building Sensor Watch and some other gadgets that are going to pop in from time to time. But for the most part, I want to talk about Sensor Watch specifically. If you look at this circuit board, there's not a lot of silicon on the board. In fact, there are only two ICs on here. U1 is the SAM-L22 microcontroller that runs the show, and U2 is a 3.3 volt power regulator. But the truth is, the regulator only really gets into the mix when you plug it in to program it. Once the watch is on your wrist, that chip is cut out entirely, which means that Sensor Watch uses this one chip, and this one chip only, to do everything that it does. There are sort of two reasons for this. One of them was I wanted to keep the BOM count low to make manufacturing affordable. But the other part of it was there's really not a lot of room for other stuff on this chip, or on the board. Once you drop this big chip in the middle of this tiny watch case, there's really not a ton of space left over. But like I was saying earlier, this microcontroller is a little computer of its own, and it's got a lot of really useful stuff built in that make it kind of ideal for a wristwatch. This is not the SAM-D21's block diagram. This is now the SAM-L22's. But they have a lot of the same peripherals. And in fact, we're going to make use of some of the things we found over there here. In fact, let's start right here with the real-time counter peripheral in a chapter I like to call Time and Time Again. You'll recall in our clock example earlier, we wanted to use a DS3231 real-time clock for timekeeping. This is a really popular RTC for a lot of projects because it is sort of wildly accurate. It's got a timekeeping crystal embedded right there inside the chip, as well as a temperature sensor. Okay, why a temperature sensor? Well, crystals oscillate slightly faster or slower depending on the temperature, and that difference can add up over time. This is a block diagram of the DS3231, and the crystal is right there at the top left. You can see where it feeds its output into some control logic, which also gets some input from the temperature sensor. At the end of all that, it generates a 1 Hz output that goes into the clock and calendar registers, which is where all the timekeeping takes place. This temperature compensation process earns it a very, very self-confident title on its datasheet, Extremely Accurate RTC. But it's not a lie. This real-time clock has an accuracy of plus or minus 2 parts per million, which means that it's not going to drift very much over time. Personally, I'd love to have this kind of temperature-compensated setup on Sensor Watch, but unfortunately, there's no room for a chip like this inside our tiny watch case. Instead, let's take a look back at the block diagram of the SAM-L22 microcontroller. Looking closely, we have a few parts that might be relevant for this. We have an external interface to a 32 kHz crystal, and we have a real-time counter that can operate in a clock and calendar mode. We have a 12-bit ADC that we can use to read a temperature value, and above it all, we have a whole heap of control logic. Okay, so here's the question. Can we coax the thing on the left into doing the things that the thing on the right does? To answer that question, let's take a look at some of the registers on the real-time clock peripheral. You have some common things you'd expect, like the clock register here with all the date and time information. But I want to zero in on register 14, which I'm going to pronounce freak core. It actually stands for frequency correction, and it has two pieces to it, a sign and a value. Okay, don't bother reading all of this. It's a note from the datasheet that explains it. And in short, this register lets us adjust the ticking of the clock ever so slightly, to the tune of just under 1 part per million per bit. The value tells it how much to correct, and the sign tells it whether that correction value should speed up or slow down the frequency. Okay. So fun story. I didn't actually do this next part. This next part came from an early backer of SensorWatch. Y'all might know him as Zeptobars on Twitter. He actually went to the trouble of characterizing the SensorWatch crystal, measuring the deviation from nominal frequency at temperatures from 5 to 40 degrees Celsius. Using the temperature sensor board in SensorWatch, his code can apply a frequency correction factor based on the current temperature, and even dither the value over time to achieve frequency corrections smaller than 0.1 parts per million. With one manual adjustment to dial in individual crystal variations, he is seeing an error of 100 milliseconds after 42 days, or under 1 second per year of drift. For comparison, this brand Seiko is one of the most accurate quartz watches on the market. It starts at $2,500, and it makes use of a temperature-compensated quartz movement. It also claims to be accurate to within 10 seconds per year, which means we might be beating this watch by an order of magnitude, again, using the real-time clock peripheral that's already inside the microcontroller that we already bought for this project. Hence the title of this section, Time and Time Again. You already bought a microcontroller with timekeeping features. If you make smart use of the peripheral that's already there, you shouldn't have to buy that feature again. Okay, that was a sort of a deep dive. So to keep it moving, this one's going to be more about wide-angle lens. Chapter 2 is about sort of a signature feature of SensorWatch, the sensor board connector. It hangs out at the bottom there, and it's what lets you add different kinds of sensors to the device using an I2C bus and 5 GPIOs. In choosing which GPIOs those were, I want to call out something important in the design phase of your board. When you start to assign pins to purposes on a microcontroller, you're likely going to be confronted with a pinmux table like this. This table tells you what each pin can do. For example, this line says that pin 1 on our SAM-L22J can be an external interrupt input in column A, or that it can work with a serial communications interface in column D. But down here, pin 12 of our chip can do a lot more than that. It can do interrupts and communications for sure, but it can also be an analog input, a touch input, or it can work with the timer counter. So when I chose these 4 pins for the sensor board connector, I did it very specifically because they have a lot of versatile applications. They give me 4 external interrupts, as well as 4 analog inputs. They can be used for serial communications, and with the timer counter peripheral on timer counters 2 and 3. They can also be used as low power inputs to the real-time clock, and with some other stuff that we're going to talk about later. Okay, the reason I bring this up is if you're planning to offer general purpose I/O to users of your product, choosing pins with really versatile possibilities is going to help you make the most of your microcontroller even after you ship your gadget. For example, this sensor board has a phototransistor and a thermistor. It uses the analog features of 2 pins to read both light and temperature levels with our ADC. It also uses the digital features of 2 other pins to enable or disable those sensors, which saves our battery power. This board, on the other hand, uses the I2C interface to talk to an accelerometer. It breaks out pins A1 and A2 as test points for a UART, which can stream accelerometer data for input, or for development or machine learning purposes. Pins A3 and A4, it uses as external interrupt pins, which can alert SensorWatch when the accelerometer experiences an orientation change or has data ready to fetch. Finally, this board claims pins A1 through A4 as an SPI interface to a 2 megabyte flash chip. Now, I have some ideas about using this chip to store train schedules, maybe like coefficients for calculating tide charts. But the point is, having an SPI interface makes a chip like this super easy to add on. My point in showing you this is all these boards are using all the same 5 GPIO pins, but they're using them for vastly different purposes. The light and temperature board is using these 4 pins, 2 digital outputs and 2 analog inputs, to measure light levels and temperature. Whereas the accelerometer board is using some of those same pins for a serial interface and external interrupts. Finally, that SPI flash board is using those exact same pins for a totally different serial communications protocol. So yeah, choosing pins with really powerful possibilities means that I've hopefully future-proofed this pinout, helping designers of sensor boards to make the most of this microcontroller in the future. Okay, I'll also add, if you're not super familiar with this whole process, there are graphical tools out there like Atmel Start that'll guide you through the pin selection process and even call out when you attempt to assign a feature to a pin that's not available for that purpose. Okay, chapter 3. And I gotta say, I really like this chapter. I call it Lights and Music. This chapter deals with one of my favorite peripherals on the SAM series of chips, the timer counter for control. It's actually similar in some ways to the timer counter peripheral, which I've circled there also in yellow. If you've ever used the analog write function on an Arduino Zero or a Feather M0, you've probably interacted with one of these peripherals, which I'm going to call the TC and TCC because it's less of a mouthful. In the case of the SAM L22, at the heart of SensorWatch, we have 4 TCs and 1 TCC. What are they good for? Well, fundamentally, the TC is a counter. It counts up or down. If you want to do something at a given interval, you can have it generate an interrupt or an event when it hits a certain value. For example, in SensorWatch, I use timer counter 0 to create a 1 kilohertz interrupt to handle USB-related tasks when it's plugged in. You can see here where I take an 8 megahertz clock and I divide it by 64 to create a 125 kilohertz tick. Then I have it overflow when it reaches the number 125. This generates an interrupt 1,000 times per second. Okay. So timer counters are great for handling a task at an interval, but they're also useful for other stuff. For example, you can have them toggle a pin when a certain condition happens, and that's where it gets fun. So let's talk about 2 modes of the timer counter. In frequency generation mode, the TC can output a signal on a pin that matches a given period. This can be really useful for generating tones. If you have the TC generate a 440 hertz square wave on a pin, and you tie that pin to a piezo buzzer, you'll get the A above middle C, like the actual note on a keyboard. Give it different periods one after another, and you can play a little song. Then we have pulse width modulation. This mode generates a square wave with a given duty cycle. This can be very useful for driving LEDs with variable brightness. A square wave that's on 90% of the time will be brighter than a square wave that's on 10% of the time. In fact, just a moment ago, we talked about the sensor board connector, and you can see how we set aside pins from TC2 and TC3 in the timer column. With PWM, you could add a whole other LED to your watch on a sensor board. And with frequency generation, you could try to match the frequency of a TV remote and make a TV be gone that shuts off televisions when you walk into a room. Okay, so we've claimed TC2 and TC3 for the sensor boards. And because this is supposed to be like a maker-friendly device, I want to make one of these peripherals available for general purpose use. I'm setting aside TC1 for that. But here's the thing. I actually have a couple of things on the board itself that could benefit from a timer counter. There's this red-green LED, which needs some dimming to blend and make different colors, and the piezo buzzer, which is inside the watch case, that I want to use to play tones. Thankfully, I still have the TCC available, but herein lies a problem. I have to pick one mode for the TCC to operate in. Earlier, we talked about different modes the TCC can use. In fact, let's put up that slide again. I can put the TCC in frequency generation mode to make my tones, or I can put it in PWM mode to dim my LEDs. But to use 2 different modes, I'd need 2 different instances, and on this chip, we only have the one TCC. The question, or the challenge, I guess, can we get away with driving 1 channel of sound and 2 channels of light using just this one peripheral? And since I'm giving the talk, the answer, of course, is you can. In fact, we can get 1 channel of sound and 3 channels of light without breaking a sweat. The trick is that the sound effect of a tone and the light effect of a dimmed LED depend on 2 different aspects of a square wave. The frequency of a generated tone depends on the period of the square wave. The shorter the period, the higher the frequency. So for example, here it's 2 square waves, 440 hertz for the A above middle C, and 740 hertz for an F sharp. The period is different for these 2 square waves, but as long as the duty cycle is around 50%, we're going to get some sound. But for controlling the brightness of an LED, the duty cycle of the square wave is the important part. Here we have 2 square waves, both at 440 hertz, but the top one has a 70% duty cycle and the bottom one a 10% duty cycle. The LED getting the 70% duty cycle will be brighter, and the one with the 10% duty cycle dimmer. The point here is the period doesn't really matter to the LEDs. Whether you're dimming the LED at 440 hertz, as in the traces at the top, or 740 hertz, like the traces on the bottom, the dimming effect is going to be the same. In code, it looks like this. When we want to play a note, we set the TCC's period to the note we want to play, and we set its duty cycle to half of that. And when we want to set the LED's color, we get the period from the TCC, and we figure out what number from 0 to that period will give us the correct duty cycle for the desired brightness or color. With that, we have the ability to derive 3 channels of light and 1 channel of sound using a single TCC peripheral. Made that for a friend who really loves Rob Zombie. Okay. So this chapter, I debated putting it in, but because it is about this very specific peripheral on this very specific line of chips. But in the end, I think I realized it's not just about this peripheral. It's about digging deep in your datasheet to make sure you're getting the most out of everything that's there. This is a gadget I made last year, a concept for a low-cost board that can fit into a little votive candle holder to glow or indicate status. It uses a SAMD11 with the TCC driving 3 red-green LEDs, just like the ones in SensorWatch. Keep in mind, because of 3 red-green LEDs, there are technically 6 LEDs here, 3 red ones and 3 green ones. As sometimes I do, I put the pinout of the LEDs onto the circuit board, and you can see here where I'm using 6 of the TCC's 8 waveform outputs to drive those LEDs. In fact, if you look closely, I arranged them in an oddly specific way. All of the red LEDs are on even-numbered channels, and all of the green LEDs are on odd-numbered channels. Now, you get the sense we should be able to control all 6 of these outputs independently, and we can, but there's something interesting about them. On the SAMD11, the TCC only has 4 control channels. Okay, I was told this next part was kind of confusing, so before we do it, I want to disambiguate something. The TCC has 4 control channels, which we can use as an input to control aspects of the wave we want to generate. But on the output side of the TCC, we have 8 waveform outputs, which begs the question, how do we control 6 or 8 waveform outputs with just 4 control channels? And the answer is, well, okay, the answer is complicated. But I want to zero in on a couple of features, just because, again, a close reading of the datasheet reveals some possibilities here. First, let's look at the output matrix. This block has to do with how these 4 control channels get distributed across the 8 waveform outputs, and the gist is there are different modes. In mode 0, you can see how it's sort of a round robin. Output 0 gets controlled by channel 0, and the same thing happens on 1, 2, and 3. But then channel 4 gets controlled by channel 0, 5 by 1, 6 by 2, and 7 by 3. The outputs essentially repeat, and I've drawn this diagram, and I'm taking a sip of water because I know it's a lot to take in. Okay, on the candle, this gives sort of independent control of all 3 LEDs. But if you look closely, I can control 2 of the red-green LEDs independently, top right, and top. But the brightness of the bottom left one on channels 4 and 5 is tied to the top one on channels 0 and 1. Those LEDs are doing the same thing. Okay, then we have mode 1, which is sort of a shorter round robin. Channel 0 controls all of the even-numbered channels, and channel 1 controls all of the odd-numbered channels. In this mode, channels 2 and 3 get ignored entirely. Channels 0 and 1 are driving all of the outputs. But because I made all my red LEDs even and all my green LEDs odd, I can control all the reds with channel 0 and all the greens with channel 1. This lets me set a color across all of the LEDs using just 2 outputs. 2 channels, rather. Precision. We can also use this in conjunction with another feature of the TCC, the pattern generation unit. This piece allows us to override any of the 8 outputs with a constant value. When we do this, the control channels are controlling the overall color of our LEDs, but the pattern generator is responsible for dimming the individual outputs. This lets us twinkle each LED independently. Here, I've used control channels 0 and 1 to set a nice yellow hue over the entire candle, and I'm using the pattern generator to tweak each LED's brightness specifically. This actually helps to explain mode 3, which just puts channel 0 on all of the outputs. It's not so useful for the candle, but if you were controlling 8 individual LEDs, you could have channel 0 control the overall brightness, and then the pattern generator controlling effects like fading or sparkling on each individual LED. Finally, there's also mode 3 here, which I have to confess I have not used yet, but it does intrigue me. It puts channel 0 on one waveform output and channel 1 on all of the others. The datasheet says it's aimed at controlling LED strings with a boost stage. The idea is channel 0 controls the switching of a boost converter, and channel 1 controls the overall brightness of all the LED strips. Then they're saying you can use the pattern generator to control effects on each one. This got me to thinking, in the past, I have definitely gone out and bought a chip to boost a voltage. But really, all that chip would be doing is switching an inductor and, getting some feedback, presumably through an ADC. But again, we already have one of those. Can I use my microcontroller as my boost converter? And the answer may surprise you, or it may not. Maybe you've done this before. But either way, a deep read of the datasheet reveals a ton of possibilities for this TCC peripheral. I know we used it for lights and music in the last chapter, but the point of this chapter is to go deep and see if the peripherals you have can be used in creative ways to accomplish your goals. Okay, that was a big couple of sections, so now a couple of quick hits. Back at the beginning of this project, when I was first sharing the sensor board concept, someone reached out to suggest that I implement a sensor board with a true random number generator based on avalanche noise. This is a really cool concept. It lets you generate high-quality random data using an electrical phenomenon rather than the radioactive isotope or a wall full of lava lamps. Anyway, as much as it would be fun to build a sensor board that generates random data, here in the SAM-L22 datasheet, we find that there's already a true random number generator right here inside the chip that, yes, we already bought and put on our circuit board. In fact, it's better than our homebrew RNG because it's been tested and it's guaranteed to generate high-quality random numbers that pass cryptographic test suites. So, as it turns out, getting 32 bits of random data is as simple as turning on this peripheral and reading the bits that come out. This is actually especially fun for me because one sensor watch backer used this to create a tarot reading watch face. It can do a card reading with all the major arcana or the full deck, and I love that it's using true NIST-approved random numbers for this purpose. Okay, another quick hit. This next chapter deals with something that felt necessary for this product. We have this sensor watch, and it's plugged into this sensor board, which can measure the temperature. What I'd really love would be to store some of that temperature data, log it someplace. And I know what you're thinking, add an SPI flash chip. I mean, we just learned we could do that, right? Or hey, we could use an 8 kilobyte EEPROM on the Icebird C bus. Or even better, non-volatile FRAM. But I've got a better idea. What if we could store the data right here on the same chip we've already been using? Well, as it turns out, our microcontroller has a whole EEPROM emulation area set aside. This is a special area of the flash memory on our chip that can be written to even while the main flash array is being read or programs are being executed from it. Deep in the datasheet, we can look up the exact model of our chip, which is this one, and we can see that our read while write section is 8 kilobytes in size. In this moment, we discover that the 8 kilobyte EEPROM was inside us all along.
This stuff is worth it just for that.
Thank you. In the case of SensorWatch, our firmware exposes this 8 kilobyte area as a little file system, using the aptly named Little File System project. With just 512 bytes of overhead, we get the rest of the space to store CSV files with log data, user preferences, or really whatever else we want to. And LittleFS automatically gives us wear leveling and peace of mind. What?
Wear leveling?
Yeah, LittleFS. It's on GitHub. It's you basically implement 4 functions like block erase, block write, and yeah, it'll just automatically use your flash and give you wear leveling and everything. Okay, cool, sweet, awesome. Another deep dive. In this chapter, I want to talk about saving power. Let's put up one of those block diagrams again. Looking at this block diagram of our microcontroller, we definitely see the processor right up here. As the sort of thinky part of the computer, it uses more power than some of the other peripherals, like, say, these analog comparators. And as an aside, these analog comparators are actually super fun. They're sort of like an ADC, except that instead of us querying them for values, we could just tell them to control voltages on 2 inputs. So, yeah, to compare the voltage levels on 2 inputs, and they'll sort of automatically output a digital result that tells us which is higher. So this actually isn't hypothetical. I'm planning to use this. This is an art installation that I'm collaborating on with a friend, Zach Landsberg. And as a side note, if you're curious, buy me a beer later and ask me about the Republic of Zakistan. Okay, but I digress. The thing of it is, this Subway Serpent has signs and LEDs that light up. We need for them to turn on at sunset and to turn back off during the day. To do that, we might install a light sensor, which would give us a curve like this, where high light levels are near 255 and low light levels are near 0. Now, I think the standard like Arduino sketch version of this is to just run in a loop with a delay, sampling the brightness repeatedly to see if it's below a certain threshold, and then turning the art on when it is. But with an analog comparator, we can just give it a threshold level. In this case, I'm saying the sun is setting at brightness level 48, and the analog comparator will output a logic high signal whenever that condition is met. This turns the if-then from our Arduino loop into an automatically updating digital output, indicating whether the art should be on. Going back to the block diagram, it occurs to me that it would be nice if the analog comparator could handle our conditional logic, and we could turn off the processor completely during the daytime. Instead of running in a power-hungry loop, we're basically letting the lower power analog comparator handle this check for us. This is actually a very common need. It's so common it has a name, sleepwalking. A lot of peripherals have this bit called run standby, which keeps them running even when the CPU enters a low-power standby mode. In standby mode, the CPU is halted. along with any other peripherals that you haven't set up to run in standby mode. This is a great way to conserve your power budget in a battery-powered or energy harvesting project. If we do this, we can put the processor to sleep completely and only wake up the Subway Serpent when we absolutely need to. Once you have your peripherals set up to sleepwalk, entering standby mode is as simple as setting your desired sleep mode and then telling the system that you want to wait for the next interrupt. It then hangs out in standby at that wait for interrupt line until one comes in. Okay, while it's waiting in standby, your microcontroller is consuming very little power. How little? Let's take as an example the SAM D21 in the Feather M0 Basic. In active mode, computing something or doing work, you're looking at 3 to 5 milliamperes of current consumption. In idle mode, while the CPU is awake but not doing anything, you're looking at 1 to 2 milliamperes. How about standby mode? How much does that help? Well, if we have the real-time clock running, we're looking at about 4.1 microamperes, which comes out to a fraction of a milliampere. And without the RTC, you're looking at 2.7 microamperes, 3 orders of magnitude difference from being awake. And just to put some napkin math to it, in idle mode, consuming 1 milliampere, we'd chew through a milliampere hour in about an hour. But in standby mode, consuming 2.7 microamperes, that same milliampere hour would carry us for 370 hours. I don't know about you, but for me, this sparks joy. So yeah, if you're designing a battery-powered gadget, you're going to want that power savings. Putting the CPU to sleep and sleepwalking 1 or 2 peripherals that can wake you up is a great way to make gadgets last a very, very long time. Okay, so we talked about sleepwalking and about low power, but now let's go even lower. This is a Sharp memory display. It's a very cool, very low power display. But if you've ever tried to use one and take advantage of that low power goodness, you may have run across an odd requirement. They need to be fed a slow square wave at all times. For some displays, it's 1 hertz, for some it's 60 hertz, but either way, we do need to generate this square wave. How do we do that? Well, we just talked about sleepwalking, and yes, you can totally sleepwalk a timer counter to generate a 1 hertz square wave. But to me, that feels like a waste of a timer counter. I also see folks using the 1 hertz output from an external real-time clock, but we just decided we could probably get away without an external RTC. I suppose you could also use a 555.
Yes.
But once again, we're trying to get rid of chips, not add more. Well, what if I told you there was a secret, ultra-low power output available to you deep down at the lowest levels of your microcontroller? This is a block diagram of the supply controller on the SAM L21. So this is so low level, it actually sits below the logic of our chip, down where it's doing tasks like regulating power for the CPU core and generating reference voltages for brownout detection. But up at the top right here, it also has 2 outputs, out 0 and out 1. What are these mysterious pins? Well, the fact is, we saw them briefly before when I was talking about the sensor watch and the pins that I chose for the sensor board connector. Here in the supply controller column, which I've labeled other stuff, we have these 2 outputs. What can they do? Well, they're output pins, which means they can be driven high and low like any GPIO. But we can also toggle them when the real-time clock generates an event. And as it turns out, we can configure the real-time clock to generate an event anywhere from once to 128 times per second. By configuring the RTC's event generator, we can generate a square wave of 64 hertz or slower, get this, without spinning up any other peripherals. This makes it an extremely low power output. In fact, it's so low power, it even runs in backup mode, the lowest of low power modes. So this is the final frontier of low power modes for the SAM series of chips. In this mode, your microcontroller shuts down not just the CPU, but everything that's not in the backup power domain. What kinds of things are in that backup power domain? Well, it's not a lot. It's sort of the skeleton crew of your microcontroller, but it does include the supply controller, which is enough to give you a couple of low power outputs and a few low power inputs that you can use to wake up from this deepest of deep sleep modes. In fact, this deep sleep mode is so deep that I had to make another one of these slides. Before, we were looking at the power consumption of the SAM D21. Now, let's take a look at the SAM L21, which is optimized for low power and includes this special backup mode. In active mode, calculating something, we consume it from 2 to 4.5 milliamperes. In idle mode, 0.6 milliamperes, respectable. Standby mode, we're in the single-digit microamperes, which I would categorize as impressive. But in backup mode, we're looking at power consumption on the order of nanoamperes. This is a staggeringly low level of current consumption, and to be clear, in this mode, with these outputs, we could still display a message on this sharp memory display with a backup output toggling dutifully at 1 Hertz, feeding it a square wave that's going to keep it happy. Okay, chapter 9. Now that I'm talking about backup modes, I want to go back to something that I glossed over a few minutes ago. Earlier, I showed you the DS3231, and I mentioned that it was a really popular real-time clock because of its high level of accuracy. That much is true, but I also only showed you the front side of this breakout board. If I'd shown you the backside, I would have shown you the other reason it's so popular. It has a battery backup feature, meaning that even if the power fails on your main gadget, a coin cell can keep the clock ticking. This means that once power is restored, the time will still be set. Wouldn't it be nice to have that feature on our microcontroller? Well, depending on which microcontroller you choose, you might be able to get that feature too. Let's recall this diagram from before, where we pointed out the low power outputs. Here, I'm pointing out a low power input for a backup battery. This is just a regular old GPIO pin, port B, pin 3, but you can twiddle some registers and configure it to work as a coin cell backup. When you set it up like this, a battery backup power switch can detect that the board's main power is cut out and automatically switch over to the backup domain. Let's recall what's in that backup domain. Well, what do you know? It includes the real-time clock. That is enough to ensure that even after main power dies, your clock can keep ticking and your gadget will still have the right time when the user plugs it back in. In fact, if you have one of these Adafruit PiBadge or PiGamer boards, you can just try this feature out for yourself. The battery backup pin, PB03, is tied to the stemma port D2. To be clear, you'll have to do some low-level setup in the supply controller, but once you do, you should be able to not just keep the clock ticking, but also retain 32 bytes in registers and up to 8 kilobytes of data in backup RAM, depending how much you want to tax your coin cell. Okay, for this penultimate chapter, I will admit, I have not implemented this yet, but I want to do it soon, so I'm sharing it here because it does tie into the topic at hand. One of the things I really want to play with SensorWatch is getting data into and out of the watch. Unfortunately, it's sort of hermetically sealed in a watch case, and there's no way to connect electrically with the insides from the outside. I have considered a few options here. One temptation is to build a Bluetooth accessory board, and it sounds great in theory, but in the end, I fear wireless radio might chew through too much of our coin cell, and it is a pain to replace. One SensorWatch backer has built a really cool chirpy watch face that uses the piezo buzzer to beep out data. Here's what it sounds like. I really like this. But since it uses the piezo buzzer, we can only use it to get data out of the watch. We can't use it to put data into the watch. But if we're talking about things that can get into and out of the watch, light can do that. We know this because our backlight works. So I've got two ideas here. Either we add an infrared LED and use the IRDA mode of the UART peripheral, or we encode data using Manchester encoding and blink it in and out. Okay, Manchester encoding. I'm not going to go into like a deep dive here, but the gist is it encodes a clock and a data input into a single signal that toggles reliably often. On the other side of this signal, you can recover the clock and decode the data. And as it turns out, you can take the plain old clock and data outputs of something like an SPI interface and turn them into Manchester encoded data using nothing more than a few basic logic gates. Question: can we fit these required logic gates onto our tiny SensorWatch accessory board? And the answer, of course, is it's a trick question, because there's yet another peripheral that can help us out here. Don't bother trying to read this whole paragraph. I just want to show you the heading. This is the configurable custom logic peripheral on the SAM-L22, and it has some really useful features if all you need is a few logic gates. It has 4 lookup tables that can implement simple combinatorial logic like ANDs and XORs, as well as sequential logic like the D-latches that we saw in the patent diagram, all without taking up any CPU time. The inputs to these lookup tables can be GPIO pins or events, or the outputs from an internal peripheral, a peripheral like the serial communications interface. So I'll be the first to admit, I have not yet been clever enough to implement this on SensorWatch, but this is a screenshot of a video from Microchip. This video is demonstrating a Manchester decoder on an Atmega chip using the very same CCL peripheral that we have on the SAM-L22. So even if I haven't done it, I get the sense that it's possible. So I think the lesson to take from this chapter, and I don't think it's a lesson that I really even learned until I was writing this chapter, is to some extent, it never ends. I've been working with the SAM-L22 at the heart of SensorWatch for more than 2 years now. I've shipped 1,500 boards with the SAM-L22, and I'm at the helm of a SAM-L22 project with more than 3 dozen contributors. To be clear, I'm at the point where I'm up here giving a talk about it. And even so, I'm still learning new ways to make the most of this microcontroller, even today. Okay, for this final chapter, I want to go back, way back to the beginning of our talk and that LCD clock gadget that we were brainstorming. Offhand, I casually suggested that we use a SAM-D21 as the brains of our product, but the truth is, different microcontrollers have different sets of skills. The SAM-D21 is an all-around solid performer, and it has diverse peripherals that make it a Swiss Army knife, sort of a Swiss Army knife for a lot of applications. But if you're making a low-cost board, you might not need all of those features. You might be able to get by with a SAM-D11, which is a lot less expensive. It has less memory, but a lot of the same peripherals, and it might lower your BOM cost significantly. Having said that, if you're making something LCD-oriented, like SensorWatch, the SAM-L22 might be your jam. It doesn't have a DAC, but instead it adds a segment LCD interface that can talk directly to LCD glass without the need for an external driver chip. But if you're aiming for something more analog-oriented, a chip like the SAM-L21 might help. For me, this chip's killer app is the 3 integrated op-amps, which could allow for advanced signal conditioning and amplification without the extra expense of an external op-amp chip. Finally, I'd be remiss if I didn't mention the SAM-D51, which is an absolute monster of a chip. It's like the SAM-D21, but everything it has, the SAM-D51 has more of. 2 DACs, 2 ADC peripherals, plus options for CAN bus and Ethernet if you get the SAM-E. It can also even interface with low-cost camera CCDs, and it has more advanced communication interfaces and cryptography features. Finally, it also has that supply controller peripheral, so it can do battery backup and it can enter those low-power modes that we talked about. I guess the point I'm trying to get at is to cast a wide net and look for chips that have useful peripherals for your specific use case. If you can do that, you may find yourself using fewer chips and sweating less over BOM costs and parts shortages. Okay. With what we've learned, let's go back and take a look at our clock gadget. We said we wanted accurate timekeeping, and we were going to use a big, expensive DS3231 for that purpose. Instead, by using the built-in RTC and an inexpensive crystal, we've saved board space and reduced BOM costs. With a little bit of effort characterizing that crystal, and the BME280 giving us temperature data, we can really dial in the frequency correction, giving us Grand Seiko-style accuracy at a fraction of the cost. We liked the NeoPixel for status indication, but we didn't like its quiescent current draw. Instead, we can use a less expensive RGB LED and drive it with 3 channels of a TCC peripheral. As an added benefit, when the LED is off, its quiescent current draw is 0. We mentioned wanting an I2S DAC for generating sounds for an alarm, but instead, we could use a piezo buzzer and drive it from a TCC pin. This is admittedly not as versatile as our DAC, but a simple piezo buzzer is something we know is going to be in stock. We also talked about using 2 chips to drive our logic and our display, a SAM-D21 to handle the logic, and an LCD driver chip to talk to the glass. Instead, we can use a SAM-L22 microcontroller, which has the LCD driver right there on the chip. This cuts down on BOM costs, because we've removed a whole chip from our design, but it also cuts down on manufacturing costs, because it's 1 fewer placement you're going to get charged for. Not only that, moving to the L22 lets us add that same battery backup mode that the DS3231 offered us, keeping the clock set even if the main battery dies. Moreover, with what we've learned about standby and deep sleep, the main battery is likely to last much longer, which will spark joy in the people that use it. We can even get some bonus features out of this deal. Like with the SAM-L22's EEPROM emulation area, we can now add a little storage area for things like time zones, unit preferences, or logged environmental data. This makes the device even more useful without adding a single extra part to the board. So, to answer the question of can we do more with less? You bet we can. So, as this talk draws to a close, I just want to reiterate that by thinking deeply about the chip you put at the heart of your designs, you're likely going to be able to make products that are more affordable and easier to send out into the world. And isn't that the point, really, to send a vision out into the world? That's what matters. Okay, so that is my talk. I hope it helps you all as you embark on building microcontroller gadgets. Thank you. Before I go, I just want to share my contact info in a couple of places you can see my stuff. First up is the Oddly Specific website, which has documentation and resources. There's also shop.oddly specific, where you can buy some of these products, like sensor watch screen things, which are little stickers that let you dress your sensor watch in costume. I actually brought some with me. Flag me down if you're interested. You can also follow me on Mastodon. And then I don't want to leave without mentioning Gossamer. I did a lot of the demos using this. It's a low-level framework I'm hacking on to build low-power, cross-platform firmware for the SAM-D and SAM-L series of chips, kind of ironing out some of the registered layout differences and whatnot. It's very early days still, but I am using it in some of my projects, and I'd be stoked for folks to take a look and see if it makes sense for theirs. With that, I think my time is up, so I want to say thank you and have a great rest of your teardown.